last session of our lecture, Linear MPC, Linear Model Predictive Control, I would like to make a brief overview and mention about the parameters that we can use to tune or get better performance out of the MPC formulation. And here I have written down a general formulation for MPC. So we have states, we have inputs, we have some relaxation parameters, epsilon, k, and we have some terminal term also here, terminal cost function value. As you can see, the prediction and the control horizon is n, and we have our discrete system, input constraints, state constraints. X0 is given, but of course I said that it needs to be updated in each time frame, in each cycle, and we have the epsilon term, which should be equal to or greater than 0. Okay, that's fine, but quite lots of terms lying on the background. As designer, we should be aware of them, and we should be aware of the consequences that they bring to our overall system performance. And I would like to briefly mention about some of the important ones today. The first one is the control interval or sampling time. Since this optimization routine should be done in every time cycle, in every sampling time, let me say, the selection of sampling time for your discrete system is quite important. So, of course, you would like to pick a big number, but in terms of finalizing the optimization routines on the background. But when the sampling time gets bigger, then we may face more perturbations out of our system. So from the sampling point of view, it makes sense, or it's the desire to keep the sampling time short. But on the other hand, we have a trade-off here in terms of finalizing the optimization actions. This sampling time should be relatively big. So there's a trade-off between here. So it should be as small as possible, but it should also let you to execute the optimization tasks on the background. And of course, it depends on the system that you are working. For example, if you are designing a model predictive control for autonomous driving, then the sampling time should be milliseconds level, like 10, 20, 40 or so. But if you are, let's say, considering the temperature control of a room or any chemical reaction or so, maybe this could be a bigger value, like in seconds or even in minutes time frame. Okay, so this sampling time is the first thing that I could mention. The second one is control and prediction horizon. Horizons. NP and NU. You couldn't directly see it here in this formulation because they are equal and they are let's say equal to n in this formulation. But I could write some recommended values here, and u should be greater than 2, and additionally it's also desired not to keep the prediction horizon too much, because when you increase the prediction horizon to a big number, let's say 100, 1,000 or so, there are two consequences for you. The first one, you decrease the aggressiveness of the system. So the system believes that it has more time to converge or so, and then this may result relatively poor performance for you. This is the first one I would like to mention. The other one is you need to complete next 50 or 100 states of your system. This also puts some extra burden on your computational effort. So it's because of that, from the practical perspective, you should also bound the prediction horizon to a logical number. Okay, so the other, let's say, tuning parameter that I could introduce you is the weighting matrices. And in this formulation, they are Q and R. Okay, so let's also add this additional epsilon term here and the terminal one. So, but you may not face them in every type of formulation. Okay, they are important and maybe even the most important factors because they have a direct influence on the overall result of your system. So when you, for example, let's say I have x1, x2, and u1, and I have such a formulation here. I mean, this is in matrix and vector formulation, but I'm going to write it in a scalar form, like, let's say 5x1 to the squared 1 plus 10 x2 squared plus u, let's say 1 squared. Okay, so in this case our weighting factors are 5 for x1, 10 for x2, and 1 for u1. This says something to us. So for example, when I only compare the states internally, this says to me that my second state is more important than my first state because the weighting factor of it is greater than the first one. So when this makes 1 unit error, then this results in the cost function 10 units. If the same happens for x1, this results in the overall cost function as 5 units. You see? So in this way, we are telling our algorithm that please decrease the error on the x2 side more if you can. And on the other hand, so as you can see, both of the states' weighting factors are greater than the u1, which is my input signal. By this way, we are also telling our, let's say, MPC program formulation that you are free to use the input signal if required, okay? Because if this input deviates from my desired value, it's only affecting by 1 unit the overall cost function. But, for example, if it's instead of 1, if it would be 100, this means that use the input signal or control signal as low as possible, because if it deviates from the operating point 1 level, let's say 1 unit, this results in the overall cost function 100 units, okay? So in this new formulation, the state's error became less important relatively, but everything is relative to each other here. As you can see, the meaning of the numbers are only meaningful when you compare it with the others. For example, if I put 1 0 to all of them, it would only increase the last cost function value that you get. Instead of, for example, 100, you will get 1,000. Okay, so this is also important. And the last thing that I would like to mention is the equal concern for relaxation. So this is also a kind of nice feature that you can use if your problem formulation is compliant with it. For example, so this shows itself here. So we can add a new select variable to soften or to relax our initial constraints, but with the cost of adding more value to my cost function. So, but this is also a kind of nice tool to be used. So, all in all, today we made an introduction to model predictive control. Even though this approach is suitable for nonlinear systems, also nonlinear systems, today our focus was more on the linear side because the linear approaches were quite, let's say, robust and well established nowadays. And if we can define our model in a linear formulation, it's quite straightforward to get some nice results, but of course we should also consider lots of other parameters on the background, and this comes with an experience. It's because of that I strongly recommend you to go back to the exercises of this lecture and solve them so that you could increase your level of knowledge in this area even more. So this is more or less all for today. In the next lecture, we are going to step into the nonlinear side of the model predictive control.